Every year, over 600 million tons of scrap metal are recycled worldwide. And it is from this that the heart of a railway wheel is born. Steel that can withstand a pressure of 145,000 pounds per square inch. Imagine rusty cars and old beams in a fiery dance in an electric furnace are transformed into a molten lake of metal. But how does this chaos become a perfect wheel, capable of carrying thousands of tons across continents? In this video, we will reveal the secret of creating a railway wheel, from volcanic smelting to the secrets of heat treatment. Watch until the end, and you will learn a stunning fact that will change your perception of trains forever. It all begins in the recycling yard, because the heart of a railway wheel is steel, 100% made from recycled raw materials. Carefully selected scrap metal, old cars, beams, industrial equipment, is loaded into a giant ladle and heads to an electric arc furnace. This is a true industrial volcano. Amidst a deafening roar and dazzling flashes, 3 massive graphite electrodes are lowered to the scrap. An electric current of such strength is passed through them that it creates an arc with a temperature reaching 3,000 degrees Fahrenheit. In a matter of hours, tons of solid metal are transformed into a boiling, sparkling lake of molten steel. During this process, metallurgists take samples, analyzing the chemical composition in a laboratory. Based on these analyses, precisely measured portions of alloying elements are added to the melt. Manganese for wear resistance, silicon for strength, carbon, and vanadium. The goal is to obtain a unique chemical recipe for steel, optimized for the extreme operating conditions of a railway wheel. When the steel reaches the ideal composition, the furnace is tilted, and a stream of white-hot metal weighing tens of tons is poured into a huge ladle. From here, the stage of shape creation begins. The ladle is moved over a row of cylindrical graphite molds. A bottom pouring method is used. The metal is fed into the molds from below through a system of channels. This is done to reduce the turbulence of the flow and prevent slag and other impurities from entering the casting, ensuring maximum purity of the future wheel. For about 20 minutes, the steel solidifies, and the hot, still red cylindrical blocks, called blanks, are extracted from the molds. This is just a rough hint of the future wheel. Now begins the stage where brute force transforms the blank into a refined engineering product. The blank is heated again in a furnace to a plastic state, approximately to 2,250 degrees Fahrenheit, and sent under a press. This is a hydraulic machine with a force of 4,000 tons. The forging process takes place in several stages. First, the press upsets the blank, making it shorter and wider. Then it is moved to the first die, which begins to form the main elements: the rim, the plate, and the hub. The next step, a powerful punch pierces a hole in the center for the future axle. After this, the red-hot blank, already resembling a wheel, is immediately transferred to a rolling mill. Here it is, clamped between several powerful rollers that with enormous pressure roll and form the precise profile of the rim and flange. This process not only gives the wheel its final shape, but also works the metal's structure, refining the grain and making it significantly stronger and more resistant to crack formation. After rolling comes the most important stage, which endows the wheel with its unique dual properties: heat treatment. The wheel must be both hard and tough at the same time. Its running surface must be extremely hard to resist wear, while the plate and hub must be softer and more ductile to absorb shocks and not crack. For this, the entire wheel is uniformly heated to a temperature of about 1,550 degrees Fahrenheit. Then, at a key moment, a special spray ring delivers powerful jets of water exclusively to the rim and flange of the wheel. This instantaneous cooling, or quenching, drastically changes the crystal structure of the steel on the running surface, making it extremely hard. At the same time, the plate and hub cool slowly, in the air, which allows them to retain a more ductile and plastic structure. After this, the entire wheel undergoes a final tempering, heating to a lower temperature, about 1,000 degrees Fahrenheit, to relieve the internal stresses that arose during quenching and make it less brittle. Even after such complex processes, the wheel is not yet ready. It has the right strength, but its surfaces are rough, and its dimensions are imprecise. The machining stage begins. The wheel is mounted on massive computer-controlled lathes. Cutting tools remove thin layers of metal, turning the rolling profile and flange to ideal dimensions with an accuracy of thousandths of an inch. The central hole for the axle is separately bored. This operation requires the highest precision, as the wheel must be press-fitted onto the axle with enormous force, creating a connection stronger than a weld. The final stage is total quality control. Safety here is an absolute priority. Each wheel undergoes a series of non-destructive tests. It is inspected with ultrasound to detect any hidden internal defects, such as voids or cracks. The surface is checked using magnetic particle inspection to detect microscopic cracks invisible to the eye. Laser scanners and sensors check every dimension. And only after the wheel has passed all these checks does it receive its marking and is considered ready. Thus, the journey from rusty scrap to a shiny railway wheel is complete. It is a quiet triumph of engineering that allows millions of tons of cargo to safely cross the continent. Statistics on rail transport in the US illustrate the loads that each wheel withstands. American railroads move about 1.5 billion tons of freight annually. The average weight of a freight train is almost 4,000 tons, and its length can exceed a mile, with 100 to 150 cars. The weight of a standard loaded freight car can reach 286,000 pounds, and in some cases, 315.5 thousand pounds. This weight is transmitted through 8 wheels, creating a static load of over 35,000 pounds on each wheel. At the point of contact between the wheel and the rail, the pressure reaches high values. The contact area is comparable to the size of a dime. In this area, the pressure averages 90,000 pounds per square inch, and peak values can exceed 145,000 PSI. Such loads exceed the yield strength of the steel, causing elastic deformation of the metal at the point of contact with each rotation. The standard diameter of a wheel for 100-ton capacity freight cars is 36 inches. For 70-ton cars, 33 inches. The weight of a 36-inch wheel is about 800 pounds. During its service life, an average freight wheel travels from 500,000 to 700,000 miles. There are over 1.5 million wheels in service on the US rail network. Each of them undergoes ultrasonic and magnetic particle inspection to detect internal or surface defects. Standards developed by the Association of American Railroads regulate all parameters, from chemical composition to rolling profile tolerances, to ensure safety and reliability in operation. You have to agree, there is something romantic about trains. And now you know exactly what kind of wheels are making that clatter. Imagine a plant spread out over 11 million square feet, where thousands of specialists work every single day to assemble an aircraft made up of more than 4 million parts. Here, in Toulouse, France, giants of the sky are born, from the legendary A380 to the cutting-edge A350. Parts for these aircraft come in from all over the globe. Wings from Britain, the fuselage from Germany, and engines from the United States. This is not just a plant. It is the heart of European aviation and a true marvel of engineering. And now we are going to take a look inside. The Airbus plant in Toulouse covers an area of over 11 million square feet. Now, that is an impressive size for any manufacturing complex, and especially so in the aviation industry. This plant produces not only the A380, but also other aircraft models from the company, like the A350. To produce these technological wonders, Airbus uses more than 2,000 workstations equipped with the very latest technology. This plant is the heart of Airbus aircraft production and a complex logistics hub, where every stage of aircraft manufacturing is its own form of art. The Airbus plant in Toulouse was actually founded way back in 1946 under the name Aerospatiale. Initially, it was a French company specializing in aviation manufacturing, and it laid the groundwork for the future Airbus plant. All the early stages of the plant's operation involved creating aircraft for both military and commercial needs. The Toulouse plant was strategically chosen for its location, which provided convenient access to transportation and logistics routes within France and across Europe. Originally, the plant focused on developing smaller aircraft, but over time, it expanded its capacity and implemented new technologies to produce large passenger aircraft. In 1970, the company Airbus Industry was established, a consortium that brought together 4 major European aviation companies: Aerospatiale from France, Deutsche Airbus from Germany, Construcciones Aeronauticas from Spain, and Air Italia from Italy. From that point on, the history of the Toulouse plant became closely linked with the development of the aviation industry in Europe. This is where the production process for Airbus aircraft began. Aircraft that would become significant competitors to giants like Boeing. Over the following decades, the Toulouse plant expanded multiple times as aircraft production really picked up speed. In the late 1980s and early 1990s, the plant became the main hub for producing aircraft like the Airbus A300, the first certified wide-body aircraft, and the A320, one of the most popular aircraft in the history of civil aviation. Over time, the Toulouse plant became the primary production center for models like the A330, the A340, and the A380, that huge double-decker aircraft that became a symbol of Airbus. In the 2000s, the Toulouse plant underwent major changes and modernization to handle the production of newer models, like the A350, which was introduced to the market in 2013. For this purpose, new assembly halls were built at the plant, including large facilities for assembly and testing, along with new automation systems to boost production efficiency and precision. Manufacturing the Airbus A380 is such a complex and detailed process that it requires innovative methods and technologies for its assembly. Just imagine, each aircraft produced at the plant consists of over 4 million individual parts. These parts are supplied from all around the world, from China to the United States. For example, the main fuselage components come from Germany, the wings from Great Britain, and the tail section from Spain. That is right, the Toulouse plant primarily handles the final assembly of the aircraft. This is standard practice for major aircraft manufacturers. Major engine manufacturers, like General Electric and Pratt & Whitney, supply the powerful jet engines for Airbus aircraft. Additionally, various aviation systems and components arrive from the United States. China is a key supplier of various metal parts, plastic components, and other materials for the aviation industry. Furthermore, Chinese companies provide certain aerodynamic parts. Other parts, including structural elements and fuselage details, are supplied by various European countries, such as Germany, Italy, Spain, and Great Britain. Well-known Canadian companies, like Bombardier, also supply components for different Airbus models, notably for the A220. After being manufactured, these parts are transported to the plant in Toulouse, where they are assembled into a single, complete unit. This often takes several weeks, and the large components are transported using specialized methods, like ships or air transport. The Airbus plant in Toulouse covers an area of 11 million square feet. It is one of the largest aviation manufacturing sites in the world. First, inside the plant's enormous assembly halls, the aircraft fuselage is put together. This is the main body of the aircraft, composed of several large segments that are delivered separately. Each fuselage segment is a major part of the structure, joined together with the others using cranes and specialized assembly machines. A crane lifts the parts, and they are carefully connected using special bolts and welding techniques. This is how the frame structure begins to take shape. Although it is not yet in its final form, once the main fuselage sections are assembled, the wings are brought into separate areas for installation. These wings are heavy, and their installation also involves the use of hydraulic cranes. When the wings are ready, they are attached to the main fuselage structure. Special attention is paid to this stage because the join between the fuselage and the wings is a critically important part that affects the aircraft's aerodynamics and safety. The installation of all the necessary systems, electrical, hydraulic, and avionics, also happens during this phase. Parts are integrated in special clean rooms to prevent any damage or contamination. This is a highly precise process, as all the elements, like cables, pipes, and computer systems, must be correctly positioned within a limited space. Robotic systems are often used at this stage for the precise placement of these elements. Once the aircraft structure is nearly complete and all internal systems are connected, it is time to install the engines. This is another critically important step, as the engines play a significant role in the aircraft's overall stability. Large hydraulic mechanisms and cranes are used to lift the heavy engines and precisely attach them to the aircraft structure. This also demands a high degree of precision and care. As soon as the aircraft is assembled and the engines are in place, it undergoes a series of tests and checks. On the ground, they conduct tests on the braking systems and check the aircraft's response to mechanical stresses. All these operations take place on enormous testing grounds, which allow for trials involving various loads and speeds. At the same time, the functionality of all the aircraft systems is verified. The testing area itself covers about 2 million square feet. After all the tests and adjustments are done, the aircraft moves on to the finishing stage, where it gets painted and the final details are added: window sealants, stripes, logos, and other design elements. Before the paint is applied, the aircraft is thoroughly cleaned to remove any contaminants, grease residues, or dust. Following this, the metal surface is treated to ensure better paint adhesion. An important step is the application of an anti-corrosion coating, which protects the aircraft body from oxidation and other harmful factors. This coating is applied using special sprays or spray guns to create a uniform protective layer. The aircraft is then painted in several layers. Most often, special polyurethane paints are used, which provide a durable, resistant coating. These are applied using rotary atomizers, which allow for even distribution of paint across the entire surface. The aircraft is placed inside a special painting hangar, sort of like a large enclosed area, where the necessary temperature and humidity levels are maintained to ensure proper paint adhesion to the surface and facilitate quick drying. After the base color is applied, a top coat is added, which provides extra protection against atmospheric elements and also gives the aircraft a glossy finish. This layer also adds resistance to ultraviolet rays, preventing the paint from fading in the sun. After painting, the aircraft are inspected for any defects. If any cracks or bubbles appear in the paint, they have to be corrected. In the final stage, airline logos or special liveries are applied to the aircraft. This might involve not just applying paint, but also installing special decals or applying a protective film to the surface. This process can take up to several weeks for a single aircraft, depending on the size and complexity of the livery. In total, painting a complete Airbus aircraft requires about 3,300 pounds of paint. The process of installing the cockpit is one of the most complex and precise operations. The aircraft cockpit, especially in models like the A350 or A380, contains hundreds of different sensors, control systems, displays, and other technical elements that must be precisely configured. Altogether, a cockpit can contain up to 5,000 different parts. Interestingly, the assembly of the cockpit takes place separately from the main aircraft body. This is done in special workshops where the cockpit is fully equipped before being transported for final integration into the aircraft. The entire cockpit installation process takes several days and demands the highest level of precision, because any malfunction in the control or navigation systems could lead to serious problems during the aircraft's operation. Another crucial aspect is the integration of avionics, which are the aircraft's electronic control systems. These systems allow pilots to monitor flight parameters, engine status, the situation in the sky, and perform other critically important functions. Installing the avionics takes anywhere from several days to several weeks, depending on the complexity and type of the aircraft. More than 10,000 people are involved in the aircraft assembly process, including engineers, technicians, testers, and other specialists. The production cost for a single A380 aircraft is around $445 million United States dollars, making this project one of the most expensive in the world of aviation. Just for the development of new technologies, and the improvement of automation processes, Airbus spends millions of dollars every year. Every hour, over 4.5 million tires are discarded worldwide. But in Nigeria, a country with over 220 million people, old tires are not just trash. They are a currency for survival, an underground business, and even art. Here, worn-out rubber doesn't go to a landfill. It's taken apart, rolled on bicycles, cut by steel jaws, and baked into colorful tiles. How did poverty, ingenuity, and chemistry create a whole shadow industry? And what unexpected secret is hidden in one of the largest pyrolysis furnaces in Lagos? Watch until the end, and you'll see what they probably don't show in textbooks. Nigeria is the most populous country in Africa, home to over 220 million people. For many of them, a car is the primary means of transportation and doing business. Millions of passenger cars, minivans, trucks, and motorcycles travel the country's roads daily, inevitably wearing out their tires. The more vehicles, the larger the flow of used tires. The condition of roads in many regions of Nigeria is, to put it mildly, far from ideal. Numerous potholes, ruts, gravel surfaces instead of asphalt, and the general neglect of the road network lead to extremely rapid and aggressive tire wear. A tire that could last 40 or 50,000 miles in countries with high-quality roads might become unusable 2 or even 3 times faster in Nigerian conditions. A significant portion of cars in Nigeria are imported used vehicles, known as tokunbo. They often arrive from Europe, the United States, and Asia, with already significantly worn tires that require almost immediate replacement after purchase. This creates an immediate stream of old tires into the waste market. Due to economic hardships, many Nigerian drivers cannot afford expensive and high-quality tires from leading brands. They are forced to choose the cheapest options, either low-quality new tires, mainly from Asian countries, or already used tires. Both options have a very short service life, which creates a continuous cycle of buy, drive a little, throw away. Until recently, the country effectively had no established and efficient state system for collecting and recycling tires. Without proper disposal infrastructure, old tires simply accumulated in makeshift dumps, on roadsides, in vacant lots, and in water bodies, turning into a serious environmental threat. Only recently have entrepreneurs begun to see a business opportunity in this. The process of collecting tires in Nigeria is a fascinating, mostly informal, and multi-level system that operates not by government decree, but by the laws of the market and simple economic benefit. At the heart of the entire chain are thousands of individual collectors. These are often young men or people with low income, for whom collecting waste is their main livelihood. So, where do they collect them? The main source is tire shops and car repair workshops. Drivers leave old tires after a replacement. For the workshop owner, this is trash that needs to be disposed of. A collector pays him a small amount, or simply takes them for free. Collectors also literally patrol their neighborhoods, looking for abandoned tires in makeshift dumps and on roadsides. The tires are rolled by hand, transported on wheelbarrows, bicycles, or small 3-wheeled scooters. One old tire can cost from 50 to 200 naira. That's a few American cents, depending on its condition and size. It's not much, but by collecting several dozen a day, one can make a living. Collectors rarely deal directly with large factories. They sell their harvest to local middlemen. Middlemen are small entrepreneurs who own a small truck or pickup and a place for storage, usually just a fenced-off plot of land. They buy tires from dozens of street collectors. This is where the initial accumulation happens. They might collect several hundred or 1,000 tires before the batch becomes large enough for further sale. This is where those mountains of tires appear, but on a local scale. In the yard of such a middleman, you can see piles of tires that he accumulates, waiting for a good price or a sufficient volume for transport. Basic sorting might happen here. For example, separating truck tires from passenger car tires. The middlemen make their profit on volume. They buy cheap from collectors and sell for a higher price to large processors. Large recycling companies are at the top of the chain. Companies engaged in pyrolysis or the production of rubber crumb are the final buyers. These are recycling plants like Freetown Waste Management Recycle or large pyrolysis facilities. They make deals with the middleman. The aggregator loads a large truck of 5 or 10 tons and brings the tires directly to the plant. The plant accepts the raw material, weighs it, and pays the middleman by tonnage. This is where the final, professional sorting takes place. The tires are inspected, cleaned of dirt and foreign objects before being sent to a shredder or pyrolysis furnace. As soon as the tires arrive at the recycling site, they head down one of two main paths. The choice of path depends on the technologies the company possesses and the final product it wants to obtain. Pyrolysis is a method used by large industrial plants. The goal is to break down the tire into its basic chemical components to obtain industrial raw materials. Tires cannot be loaded into the reactor whole. First, they undergo tough preparation. Powerful hydraulic shears cut out the bead ring from the tire, a thick steel wire that ensures a tight fit on the rim. Then the tire is sent to an industrial shredder. The machine's steel jaws tear and cut the rubber into pieces a few inches in size, turning it into a uniform mass resembling coarse chips. The prepared rubber pieces are loaded into a sealed metal reactor. This is the heart of the entire process. The reactor is heated to high temperatures, 800 degrees Fahrenheit, but the key condition is a complete absence of oxygen. Because of this, the rubber doesn't burn. Instead, its long polymer molecules begin to break down into simpler substances. As a result of the heating, a mixture of 3 fractions is formed: a gaseous fraction, a liquid fraction, and a solid residue. After the cycle is complete, the factory obtains 3 products ready for sale. The first is pyrolysis oil, which is used as fuel for industrial furnaces and boilers. Carbon black is sold to manufacturers of paints, plastics, and new rubber products, and the steel wire is collected by magnets, pressed into briquettes, and sold as scrap metal. Another path for recycling old tires is mechanical recycling and upcycling. This path is chosen by companies like Free Recycle, which create finished consumer goods. There is no chemical reaction here, only physical transformation. The tires also go through shredders, but the goal here is to obtain clean rubber crumb of various sizes. During shredding, powerful magnets extract steel fibers from the rubber mass, and air separation systems blow out textile fibers. The output is clean rubber granules. The rubber crumb is poured into a large mixer. 2 key ingredients are added to it: polyurethane glue and pigments. The glue will bind the rubber particles together, and the pigments will give color to the future product. The resulting mixture is thoroughly mixed until uniform. The colored rubber mass is placed in metal molds of the desired configuration, for example, in the shape of paving tiles or mats. Next, the mold is sent under a hot press. High temperature and pressure activate the glue, baking the crumb into a single, durable, and elastic product. This can be bright and safe paving tiles for playgrounds, durable flooring for gyms or garages, soles for shoes, or even entire flip-flops. A separate direction is upcycling, where whole tires or their large pieces are turned into original furniture, such as tables or chairs and other decorative items. Thus, depending on the chosen path, an old, unwanted tire is transformed either into a valuable industrial raw material or a new useful household item. Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or culm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer green skin and inner nodes, leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Yanka scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family. Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home. Every year, over 9 million tons of copper scrap are recycled worldwide. That's enough to build 1,800 statues of liberty. But where do old cables, transformers, and copper wires go after disposal? What do they do with them in the heart of factories where temperatures exceed 2,000 degrees Fahrenheit? And why can recycling 1 pound of copper save as much energy as a whole house needs? If you watch until the end, you'll learn a secret you've never heard before. So, in what city did you last see a copper factory? Write it in the comments. It's interesting to check the geography. It all starts at the huge warehouses of recycling plants. Thousands of pounds of various copper scrap flock here. Thick power cables from industrial sites lie next to thin wires from household appliances. Old transformers are neighbors with remnants of construction wiring. Each element has its own story, but they all share one thing. They are ready for a new life. The first stage of recycling is careful sorting. Experienced specialists separate the scrap by type and degree of contamination. Clean copper wire is separated from insulated cables. Thick industrial cables are separated from thin household wires. This is a critically important step, as different types of scrap require different approaches to recycling. The next stage is mechanical cleaning, a true art of modern technology. Powerful shredding machines cut the cables into fragments 2 or 3 inches long. Special separators use the difference in material density, as copper is heavier than plastic and rubber, making it easy to separate. Vibrating tables and air currents finally clean the copper fragments of insulation remnants. The output is relatively clean copper pieces, but this is just the beginning. The real magic begins in the melting shop. Huge induction furnaces heat the copper to a temperature of over 1,984 degrees Fahrenheit, the melting point of copper. The metal fragments gradually turn into a red-hot, almost golden liquid. This sight is always impressive. Hard, cold pieces of metal become a living, pulsating mass. But temperature is just a tool. The main action happens at the molecular level. During melting, impurities behave differently. Some float to the surface as slag, others dissolve. Master metallurgists carefully control the process, skimming off the slag and adding special substances called fluxes, which help remove unwanted elements. The first refining is complete, but this is not the end. The molten copper is poured into special baths for electrolytic purification. This is the most precise stage of the entire process. An electric current of several thousand volts is passed through the melt. Under its influence, residual impurities, iron, nickel, zinc, lead, migrate to the electrodes and are removed from the melt. Electrolysis lasts for several hours. The temperature is strictly controlled between 2100 and 2200 degrees Fahrenheit, and the current strength is regulated with an accuracy of tenths of an ampere. Laboratory analyses are conducted every 30 minutes. Chemists check the metal's composition, tracking how the amount of impurities decreases. Gradually, the purity of the copper increases: 95%, 97, 98, 99. And finally, the coveted mark of 99.9% is reached. The purified copper is ready for forming. The molten metal is poured into special molds, ingot molds. The molds are preheated to a temperature of about 1,800 degrees Fahrenheit to avoid thermal shock. Slow, controlled cooling allows the copper to crystallize with the correct structure. Perfectly uniform ingots weighing from 50 to 100 pounds or cylindrical billets 6 or 8 inches in diameter are formed. These billets are the basis for future cables. They go to the wire drawing shop where the next transformation takes place. A wire drawing machine is a series of successively arranged dies, openings of different diameters. The billet passes through the first opening, about 3 inches in diameter, then through a smaller one of 2 inches, then 1.5 inches. With each pass, the diameter decreases and the length increases. The drawing process requires enormous effort. Powerful electric motors with up to 500 horsepower pull the copper through the dies with a force of tens of tons. The metal deforms but does not break because copper is plastic and can withstand such a load. Gradually, the thick billet turns into a thin, flexible wire with a diameter from 1/2 inch to even thinner. Each stage of drawing is strictly controlled. The diameter is measured by laser devices. The feed speed can reach 100 feet per minute and is automatically regulated. If defects appear, such as scratches, irregularities, or cracks, the process is stopped for correction. The finished wire undergoes a final quality control. Not only the geometry is checked, but also the electrical properties. The resistance must not exceed a certain value per 1,000 feet of length. Conductivity, mechanical tensile strength. All parameters must comply with strict American Society for Testing and Materials standards. After all, this wire will become the basis for cables that will transmit electricity to homes, offices, and factories. The final stage is the manufacturing of the finished cable. Copper wires are covered with insulation up to 1/10 of an inch thick, polyethylene, polyvinyl chloride, or other modern materials. Depending on the purpose, the wires can be twisted into the required configuration. Power cables for 120 or 240 volts, information cables of category 5 or 6, special purpose cables, each has its unique design. Packaging the finished product is the final touch. Cables are neatly wound onto spools, 3 or 4 feet in diameter, or placed in boxes of standard sizes. Each unit is marked, indicating the length in feet, the cross-section in American wire gauge, and technical specifications. Underwriters' laboratory certificates confirm that the product meets all American safety standards. The result of this complex technological symphony is impressive. From scrap that seemed like useless junk, high-quality cable is born. It is ready to serve for 25 or 30 years, providing reliable transmission of electrical energy from residential buildings to large industrial complexes. But this is not just a technological process. It is a philosophy of sustainable development in action. Every ton of recycled copper is a ton that does not have to be mined from the Earth's depths. It means conserved natural resources, less environmental impact, and a cleaner environment for future generations. Recycling 1 ton of copper saves about 2.5 tons of ore. The cycle is complete, but it is endless. When, decades from now, this new cable becomes obsolete again, it will return here to begin a new journey of transformation. Copper is the metal of eternity, which can be recycled an infinite number of times without loss of quality. And in this lies its true value. The production figures are staggering. Over 9 million tons of copper scrap are recycled annually worldwide. This is equivalent to the weight of 1,800 Statues of Liberty. In America, the average family uses about 280 pounds of copper in their home, from electrical wiring to plumbing pipes. 1 million pounds of recycled copper saves enough energy to power 1,000 homes for a year. This is 85% less energy than is needed to mine new copper from ore. Recycling also reduces carbon dioxide emissions by 65% compared to primary production. The largest amount of copper scrap comes from the construction industry. That's 31%, from electronics 21%, and from the automotive industry 12%. 1 pound of copper wire can be drawn to a length sufficient to wrap around a football field 23 times. Modern factories can process up to 400 tons of copper scrap per day, producing wire with a total length of over 50,000 miles. Over the last decade, the price of copper scrap has increased by 180%, making its recycling extremely profitable. Today, recycling provides 40% of the world's copper needs, and this figure continues to grow. Every year, over 300 million electric motors are manufactured worldwide, from miniature ones that spin coolers in laptops to giants that power trains, factory lines, and mine elevators. And each one of them is not just a coil of wires and iron, but a complex system of dozens of precisely calibrated parts. How is the heart of a machine born? Why is winding similar to weaving, and balancing to jewelry making? And how does one spark power a rotation that will last for thousands of hours? Let's take a look behind the scenes of one of the greatest technical processes, the creation of an electric motor. Inside every electric motor is a true mechanical electrical universe. The main components of a motor are the stator, rotor, shaft, bearings, housing, as well as a cooling system and terminal box. The stator is the stationary part, located in a circle inside the housing. It's what creates the magnetic field that makes the rotor spin. Inside the stator is a core made of layers of thin electrical steel, which reduces losses from eddy currents. In the slots of the core is a winding of copper wire, connected in a special way to create a rotating magnetic field. The rotor is the moving part inside the stator. It either has its own winding or is made in the form of a squirrel cage. Aluminum bars cast into a steel core, which form closed current loops. When the stator's magnetic field interacts with the rotor, it starts to rotate. The shaft is a rod that passes through the rotor and extends outside the housing. It's on this shaft that pulleys, impellers, reducers, or other drives are mounted. It transmits rotation to the mechanisms. The shaft must be precisely centered. Otherwise, the motor will vibrate and wear out quickly. Bearings, usually 2, 1 at each end of the shaft. They ensure smooth rotation with minimal friction. For reliability, they are lubricated with special greases or are sealed. The housing protects the internal elements from dust, moisture, and mechanical damage. It often has fins for heat dissipation or even a fan. The material is cast aluminum or cast iron, depending on the power and purpose of the motor. The cooling system, most often it's simple air cooling, a fan on the shaft drives air flows through the housing. In large industrial motors, liquid cooling or external air circulation through special channels is used. The terminal box is on the outside of the housing. This is where the power cables are connected to the stator winding. Inside, contacts, clamping screws, and sometimes temperature sensors. In the depths of the factory, in a workshop that smells of varnish, metallic dust, and warm insulation, stands a giant stator. A stationary ring with slots around its circumference. This is its core, made of thin steel sheets, tightly pressed together. In each slot of this ring will lie copper wire, carefully laid, loop by loop, turn by turn, because whether the motor will rotate at all depends on this. Before starting the winding, the stator frame is thoroughly prepared. The slots are lined with special insulating liners, like nests for the wire. These are materials that withstand high temperatures, vibrations, and electrical loads. And only when they are sure that the insulation is perfect, the winding machine is started. The machine, resembling a giant spool that unwinds copper wire from a bobbin, wraps it around guides and lays it in the slots. Everything is automated, but under the supervision of a specialist. One sharp movement, and the wire could lay with a kink or snag the insulation. And that's a potential short circuit. For powerful or non-standard motors, winding is done by hand. A worker inserts the wire in a loop, pulls it through with a tool, presses it to the bottom of the slot, secures it, and tightens it. The work is similar to weaving, but with shiny copper and immense responsibility. Each coil, and there are dozens of them, must be identical, symmetrical, and correctly oriented. After the first layer of winding is completed, interphase insulation is laid, and then the second layer is placed. The wire forms closed loops, phases, which are then connected in a star or delta configuration, depending on the motor's setup. Then, the wires are secured with strings or plastic fasteners, the tension and geometry are checked, and if necessary, adjusted by hand. And finally, impregnation with varnish or epoxy resin, so that all this doesn't shift even a micron under vibration and temperature under load. If the stator is the skeleton, then the rotor is the muscle. It moves, rotates, creates torque. It's not visible when the motor is running, but it's what drives everything, from a fan to a train. At the core of the rotor is a steel shaft, long and powerful. Around it, the core is mounted, a set of thin electrical steel sheets stacked into a cylinder. The sheets have slots. These are for the conductors. This is where the most interesting part begins, creating the winding that will make the rotor come alive. One of the most common options is the squirrel cage. Aluminum or copper bars are inserted into the slots, and both ends are cast into rings, like a hoop around a cage. This creates a closed current loop. Such a design doesn't need to be connected directly. Current is induced inside automatically as soon as the motor starts. It's a simple, reliable, and mass-produced option for industry. But if the motor is more complex, more powerful, then classic windings are used. A worker manually lays copper wire in each slot, carefully tightening it, bending it at an angle. Here, symmetry, precise geometry of the turns, and perfect insulation are important. The wire must lie right, not touching the metal anywhere, not crossing over, not being too tight or too loose. A mistake, and the motor will overheat or fail. The rotor windings are then connected in a specific sequence: star, delta, or another type of connection. Everything is secured, insulated, and sometimes varnished. The insulated ends are led out to slip rings or brush assemblies, depending on the design. After this, the rotor is balanced, as it has to rotate at speeds of thousands of revolutions per minute. Any extra 100 grams on the edge, and everything will vibrate, hum, and heat up. The result? A compact, shiny cylinder with windings of copper wire or closed bars. It will be inserted into the stator, and the magic of converting electricity into motion will become possible. It all starts with checking dimensions and tolerances. The gap between the rotor and the stator, the so-called air gap, must be very small. If it's too narrow, friction will occur. If it's too wide, the magnetic field will be weak, and the motor will lose efficiency. The rotor is mounted inside the stator via bearing assemblies. Sometimes special guides or hydraulic presses are used for this. The rotor shaft must rotate perfectly straight, otherwise everything will vibrate or break down within a week. At the ends of the rotor shaft, sleeve or rolling bearings are installed. They allow the rotor to rotate without friction. The bearings are placed in so-called end shields, which are then attached to the motor housing. All surfaces are pre-lubricated with special greases to ensure durability. The ends of the stator and, if necessary, rotor windings are led out to the terminal box. Here they will be connected in the required circuit: star, delta, or another. In complex motors, temperature sensors are installed to detect overheating before a failure occurs. The motor is now assembled, stator and rotor in the housing, wires connected, bearings in place. But it's too early to start it. First, varnishing, drying, balancing, and testing, all like a ritual before the birth of a real machine's heart. In a spacious room with a specific smell of epoxy resin, the stator windings, and sometimes the rotor, are coated with electrical insulating varnish. This isn't just for dust protection. The varnish strengthens the structure, secures the wires so they don't vibrate at high speeds, and prevents moisture penetration. Application is either by dipping in a bath or by spraying. The motor is completely submerged in a tank of varnish, then removed and left to drain off the excess. Next is drying in a thermal chamber at a temperature of 250 to 300 degrees Fahrenheit. This stage resembles baking. The varnish polymerizes and forms a hard protective film. After varnishing, the most sensitive stage, the motor is installed on a balancing stand. The system is like a huge record player. The motor rotates at high speed, and sensors detect the slightest deviations. Even a few grams of excess mass on the rotor can cause vibration that will destroy the bearings, shorten the service life significantly, or even ruin the motor. To eliminate the imbalance, engineers drill microscopic holes in the heavier part of the rotor, removing excess metal. This is almost a jeweler's craft. The finished motor is sent to the test stand. Here it comes to life for the first time. It's connected to a power supply. Rotations, noise, heat, current consumption are recorded, and efficiency and power are measured. Everything is documented. The motor's passport contains dozens of parameters. If the motor passes all tests, it's packaged, a seal is applied, and an instruction manual is added. And very soon, this motor could be working on a conveyor, in an elevator, or in an electric train, wearing down metal and converting current into motion, without rest for tens of thousands of hours. Did you know that the machines powering global industry, transportation, and our electrical grids consume energy equivalent to building thousands of the Great Pyramids of Giza every single day? This hidden power isn't just about raw force. It's delivered by some of the most massive and awe-inspiring engines ever conceived. From the dawn of the industrial age to today's modern world, engineers have chased the dream of bigger, stronger, more efficient powerhouses. Get ready to take a journey through history and dive into the incredible scale and engineering genius behind the world's most powerful and giant engines. Our journey begins in the age of steam, a time when raw pressure was king. Picture the late 18th and 19th centuries. The engines that drove the Industrial Revolution weren't small. Early steam engines were clunky, but they quickly grew into colossal machines. Think of the beam engines, towering structures in factories and mines, with massive beams rocking back and forth, driving pumps and machinery with the power of boiling water. These were mechanical giants, their sheer physical size necessary to contain the immense forces of steam pressure. As steam technology evolved, so did the engine's power and scale. Reciprocating steam engines became the heartbeat of global shipping. Imagine the engine room of a massive early 20th century ocean liner. You'd see multi-cylinder engines with pistons the size of trash cans, connecting rods like tree trunks, and crankshafts so large they needed multiple men just to inspect them. These engines were colossal, spanning multiple decks, their rhythmic pounding driving propellers powerful enough to push thousands of tons across vast oceans. They were engineering marvels of immense moving parts, powered by the simple expansion of steam. While steam dominated for a long time, the early 20th century saw the rise of a new kind of giant, the diesel engine. Unlike external combustion steam engines, diesels burn fuel directly inside the cylinder. This was a game changer for efficiency and power density. Early large diesels quickly found their way into ships and power generation. Imagine a large, slow-speed marine diesel engine built for a cargo ship. These engines are absolutely colossal, often standing as tall as a multi-story building and stretching the length of a gymnasium. Modern marine diesel engines, like some built by Wärtsilä or MAN, are among the largest machines on Earth. The biggest ones have multiple cylinders, each with a bore, diameter. Wider than a grown man is tall. Their crankshafts are multi-piece monsters, weighing hundreds of tons. These engines produce over 100,000 horsepower, enough to move supertankers and container ships carrying 20,000 containers. The sheer scale of these components, pistons, connecting rods, crankshafts, cylinder blocks, is mind-blowing, a testament to achieving immense power and torque from internal combustion. As technology advanced further, especially in the mid-20th century, the gas turbine emerged as another powerhouse. Unlike diesels or steam engines that use pistons, gas turbines burn fuel to create hot gas that spins a turbine wheel, similar to a jet engine. While aircraft engines are built for power to weight, industrial and power generation gas turbines are built for sheer output. Imagine a power plant gas turbine the size of a bus or even a small house. Modern industrial gas turbines, like those in GE's H-Class, are engineering marvels generating hundreds of thousands of kilowatts, enough electricity for hundreds of thousands of homes from a single unit. They involve incredibly complex internal components, spinning at thousands of revolutions per minute in temperatures hotter than molten lava. Their power output, efficiency, and relative compactness compared to older technologies make them the giants of modern electrical generation. Some large ships, including cruise liners, also use gas turbines for their combination of power and smoother operation. Comparing these generations of giants is fascinating. Steam engines were the pioneers, relying on brute pressure and massive physical structures. Diesel engines brought efficiency and incredible low-end torque, dominating heavy transport. Gas turbines delivered immense power density and high-speed rotation, becoming the backbone of modern power grids and high-speed applications. Each technology pushed the boundaries of materials, science, and engineering to harness energy on an ever-increasing scale. These engines, whether the visible, rhythmic giants of the steam age or the humming complex powerhouses of today, are the unseen heart of the modern world. They drive global trade across oceans, power the trains that move goods and people, generate the electricity that lights our cities and runs our factories, and fuel the massive pumps and machinery of heavy industry. They are a testament to humanity's relentless drive to build bigger, stronger, and more powerful machines. So, the next time you see a massive cargo ship, a powerful train, or simply flip a light switch, take a moment to remember the incredible journey through history and the engineering genius behind the world's most powerful and giant engines. From towering steam engines and colossal marine diesels to blazing hot gas turbines, they are the hidden giants that built our modern world. What era or type of giant engine fascinates you the most? Let us know in the comments.